This lecture is a very short introduction to redox reactions, which are basically any reaction that involves transfer of electrons from one substance to another. We've spent some time talking about acid-base reactions, and we can, if we look at partial charges for polar covalent compounds, such as acetic acid and water, we can kind of align the molecules in a way that helps us understand the chemical reaction that's going to happen. So, of course, we can put a partial negative on any electronegative atom and a partial positive on the atoms directly attached to the electronegative atoms. And we know that elements with opposite charges attract. So we can see that there's an intermolecular attraction between this oxygen on water and the hydrogen on acetic acid. And that attraction helps initiate the reaction, the acid-base reaction, where the oxygen actually abstracts this acidic hydrogen to make the hydronium ion and the acetate conjugate base. So we can kind of start thinking about mechanisms or reasons why reactions occur. But what happens if we have reactants that are nonpolar and therefore they don't have partial charges? How can we even begin to predict or speculate what type of reaction they might undergo? So, for example, hydrogen and oxygen, we know, react together to make water. But hydrogen and oxygen are both completely non-polar. And so how would we know just by looking at these reactants what reaction might occur? Before I go much further, I want to talk about one way that chemists classify reactions. If you hear whining in the back, that is one of my dogs wanting to get out. All right, so there are different ways to classify chemical reactions, but the way we're going to focus on classifies them as either acid-base, which we've talked quite a bit about, oxidation-reduction, which is what this PowerPoint is, and a lot of other texts or sources will just say other, but in many cases that is simply referring to precipitation reactions, double replacement type precipitation reactions. This isn't something you need to memorize. It's just kind of put in your head the different types of reactions. What I like most about this chart, though, is it tells the very common different types of oxidation-reduction reactions. And so combustion reactions, so when you burn something, so if we just look at methane gas, and you're probably familiar with the combustion reaction, okay? So where you need oxygen as a reactant, and in a complete combustion, the products are carbon dioxide and water. I guess it would help if I balance this, wouldn't it? Let's see. Okay, so combustion reactions are always redox reactions, and that'll make more sense later. Synthesis reactions. So if you combine two reactants to give one larger product, that is always a redox reaction. And then finally, the opposite of synthesis, decomposition. If you start with one larger substance and it decomposes into the individual smaller products, that is always that's always redox reactions. Alrighty, so a little bit more detail about redox reactions. So now if you hear panting, that is not me, I promise you. It is the whiny dog who is now in my lap. All right, so it's pretty easy to see when there are full charges involved when it's a redox reaction. So, for example, if the elements sodium and chloride combine to form an ionic compound, sodium chloride, it's pretty easy to see what's happened to each of these elements. Sodium starts out as just the neutral element, and then we know that any ionic compound really consists of the individual cation and anion, And so we can see that sodium has gone from a 0 charged neutral atom to a positive 1 charged cation. And so it has lost an electron. We say when a substance has lost an electron that it has been oxidized. Okay? So lose electron, oxidized. We can also do the similar type thing with chlorine. Starts as the neutral atom, and in the sodium chloride compound product, it has a charge of -1. So chlorine has gained an electron, and what chemists say when a substance has gained an electron is that has been reduced, which kind of feels counterintuitive. You gain something, but you're reduced, but that's what it is. So gain electron reduced. All right, so this is my favorite mnemonic. I'm going to show you another one in a minute, but my favorite is Leo says grr. Okay, so like a lion, Leo says grr. The other mnemonic that is probably more common than the Leo says grr is oil rig. Oxidation is loss of electrons, and reduction is gain. And just to point out that you can't have oxidation without reduction or vice versa. If you have one, you have to have the other. And if you haven't noticed already, the nickname for oxidation-reduction reactions is redox. All right, let's look at some other redox reactions where it's maybe a little trickier to determine whether or not they're redox if an electron has been transferred. So if you don't have full charges developed, as you do in an ionic compound, you can look at partial charges, and that will give you the same type of information. So in any polar covalent compound, as I mentioned before, you can write in partial charges. Partial negative on the more electronegative atom, partial positive on the atoms attached to the electronegative atom. And the partial charges alone will give you an idea of how electron density has shifted. So the oxygen having a partial negative charge means that electron density is shifted towards that oxygen atom. So that is our clue that the oxygen atom, in fact, has gained electrons. Remember, electrons have a negative charge, right? So that's what's given it that electron density. And so we know that the oxygen has been reduced. Okay, remember, Leo says grr, gain electrons reduced. All right, that means something has to have been oxidized. In this case, there's only one other element, it's hydrogen. We can see that the hydrogens here have a partial positive charge, meaning they have lost electrons. Okay, now they're now electron deficient, so they are the Leo part. Right, so partial charges will give you the same information as full charges. Now, obviously, you can't always use one or the other of those, and so the fail-safe way to know for sure if a reaction is redox is to assign oxidation states. Those are numbers that you give every single atom and every single reactant and product. And then what we're going to do is look at those oxidation numbers for a particular element and see whether or not that oxidation number has changed in going from reactant to product. If the oxidation number of any element has changed, it is a redox reaction. So there are some rules you need to keep in mind when you're assigning oxidation numbers. I do want to point out that oxidation numbers are not actual charges. They are kind of just a method for us to see where electron density may be shifting during a reaction. All right, let's look at the rules real quick. Any elements in their standard state, that is how they exist in nature normally, have an oxidation number of 0. So magnesium is a solid metal under normal conditions, so we're going to give it an oxidation number of 0 if it shows up in a reaction. Chlorine is diatomic and is a gas in its natural state, so it would get an oxidation number of 0. All right, if you have any type of ions, an ionic compound, any type of ions present in a reaction, the charge on that ion equals the oxidation number, which is easy, okay? So if you had sodium chloride, okay, then it's pretty easy to figure out what their charges are, right, in that ionic compound. So that means the oxidation numbers are equal to the charge. Sodium would be +1 oxidation number, chlorine would be -1 oxidation number. This is my go-to rule because it helps me figure out more complex molecules. Oxygen almost always has an oxidation number of -2, except when it's bonded to itself. Now these are called peroxides, in case you run into them. Peroxides, oxygen will have oxidation numbers of -1, not -2, but you're not going to see these very often. All right, and hydrogen is almost always +1. Again, there are exceptions. I don't think you're going to see any, but if hydrogen is ever bonded directly to a metal, the metal gets the positive charge, and hydrogen will go ahead and accept the -1 oxidation number. Alrighty, and finally, the oxidation numbers of all of the atoms in a compound must add up to be the charge on that compound. Okay, so let me say that again. All of the individual atoms that make up any compound, their oxidation numbers must add up to give you the charge on that compound. So looking at H2SO4, there's no overall charge on this compound. So we're going to assign individual oxidation numbers, and then we're going to add them all together, and they better add up to be 0, which is the overall charge on this. So let's kind of go through our rules. I like to start with oxygen because it's almost always -2. So I put the oxidation numbers for an individual atom above them. And notice that it's the oxidation number for only one of these, oxygen. If you have to do any math, I recommend doing it at the bottom in a different place. So since there are 4 oxygen and each of them have a -2 oxidation number, for my math, I'm going to put a -8 at the bottom, which accounts for all 4 oxygens. Then I know hydrogen is usually +1. I'm going to do the math below again. So hydrogen collectively contributes +2. All right, then whatever value sulfur has, when we add all of these oxidation numbers together, they need to give us 0. So it's pretty clear that sulfur has to have an oxidation number of +6 so that when we do add these together, we get 0. Okay, so that gives you a little feeling for how to assign oxidation numbers. There's one more rule I probably should have included here, and that is fluorine, the most electronegative atom on the entire periodic table, will always have an oxidation number of -1, okay? So the other halogens can actually have oxidation numbers of - or plus, but not fluorine. It's so electronegative, it will insist on being -1, and that overrules any other rules that we have here. All right, let's get some practice, both with writing formulas again, just in case you've gotten a little rusty, and with assigning oxidation numbers. So I recommend turning off the video for a few minutes, seeing how many, maybe all of them, maybe just 1 or 2 of these that you can assign oxidation numbers to, and then turn it back on and I'll work them out for you. Number 1, the first thing you should probably do is recognize what type of compound you're dealing with. Because it has a metal in it, I know it's an ionic compound. And writing the formulas for ionic compounds are a 2-step process. So potassium, I know its common charge is +1. Fluoride's common charge is -1. So when I crisscross, I can get the correct formula of this ionic compound. Now, I pretty much already know what the oxidation numbers are because that rule says the oxidation numbers equal the charge on an ion. So potassium's +1, fluorine's -1, and I am done. Let's look at the next one, which is a covalent compound. carbon dioxide. Okay, so I told you that the oxygen rule was my favorite because it seems like so many compounds have oxygen in them. So I'm going to assign a -2 to each oxygen. I'm going to do my math below. So since there are 2 oxygen, their total contribution is -4. Carbon dioxide overall has 0 charge. So I know that whatever the oxidation number is for carbon, it must add together with this -4 to give me 0. So that tells me that this carbon in carbon dioxide has a +4 oxidation number. Sulfate anion, it may be time for you to brush up on memorizing some of the more common polyatomic ions, sulfate being one of them. The sulfate ion is SO4 with a -2 charge. All right, I get asked a lot by students with polyatomics. They're like, can we just call this whole ion -2 when we're done? No. Oxidation numbers require that you assign an individual oxidation number for every single atom. And so I'm going to start with oxygen again, my favorite. Oxygen's -2. There are 4 of them, so the overall oxidation number contribution from oxygen is -8. I'm not quite sure what sulfur is yet, but I know that when I add the oxidation number of sulfur and oxygen together, they better add up to give me -2 because that is the charge on the overall compound. And so to get -2, I see now that sulfur has an oxidation number of +6. Okay, hopefully you're getting the hang of it. Potassium oxide, that is an ionic compound. So again, finding the right formula requires that you assign the common charges and crisscross. So the correct formula of potassium iodide is K2O. Okay, but again, as with any ionic compound, as soon as you have the charges, you have the oxidation numbers. So the oxidation number of potassium is +1 and oxygen is -2. There's one more left, isn't there? Sodium nitrate. It is an ionic compound. Sodium has a common charge of +1 when it's an ion. Here comes the memorizing the common polyatomics. If you memorize no other polyatomics, I would recommend nitrate, sulfate, and phosphate. All right, nitrate, NO3 -1. All righty, so now let's assign oxidation numbers. So sodium is simply an ion, so it has an oxidation number of +1. That was easy. Nitrate, now you've got to determine what each of those atoms, nitrogen and oxygen, are. So I'm going to move it down by itself so I have a little more room. And I'm going to, as normal, give the oxygen -2. Do the math below. -2 times 3 is -6. I'm not sure what nitrogen is yet, but when I add it together with -6, I had better get the charge on this compound, which is -1. So now by simple math, you can see that the nitrogen oxidation number is +5. That's it. All right, this is just a little bit of vocabulary, which some texts are phasing out because it's been historically confusing for students, but some of them are still using them, so just so that you're exposed to it. If a substance has been reduced itself, okay, what does that mean if something's been reduced? That means it's gained an electron. Now here's the part that can get a little tricky. So in order to be reduced, That means a substance, it gained an electron, right? So in order to be reduced, it caused something else to be oxidized. It had to get its electron from someplace. So whatever's been reduced is also called the oxidizing agent. Okay, whatever's been reduced is also called the oxidizing agent. And similarly, if you have something that has been oxidized, so therefore something that's losing an electron, that means that the electron that it's losing or giving away, right, giving an electron away or losing it, has to go someplace else. So in other words, whatever's been oxidized is causing something else to be reduced. So whatever's been oxidized is also referred to as the reducing agent. Now that we've learned how to assign oxidation numbers, we're going to put all that together, look at a chemical reaction, and figure out how we use these oxidation numbers to determine whether or not a reaction is a redox reaction. So let's look at this reaction with magnesium and water that react to give magnesium hydroxide and hydrogen gas. Carefully assign oxidation numbers again to every single element in both the reactants and products. In doing so, now compare the oxidation number for a particular element. Let's just look at magnesium and see if its oxidation number has changed in going from the reactant side to the product side. Well, yes, it has. Magnesium has gone from an oxidation number of 0 to an oxidation number of +2 on the product side. So what's happened to magnesium? It has lost 2 electrons. Okay, so magnesium has been oxidized. And then remember the vocabulary in the last slide. If something has been oxidized itself, it has caused something else to be reduced, so we call that substance the reducing agent. So magnesium is a substance that's been oxidized. It is also serving as the reducing agent. All right, so that means if we have something that has been oxidized, there's something else that has to have been reduced. What is it? Let's see, hydrogen is, let's see, with this hydrogen, it's staying the same, +1. And oxygen is staying the same. Aha, see something. Hydrogen is staying the same on one of the other hydrogens, but there are 2 things that the hydrogens did. And comparing the hydrogen in the reactant water to hydrogen gas on the product side, I can see now that to do that, hydrogen has gone from a +1 oxidation state to a 0. So hydrogen has gained an electron. Therefore, hydrogen has been reduced. And remember that vocabulary from a couple slides ago. Anything that has been reduced is also called the oxidizing agent. Let's do a couple of quick practice. So if you'd like, this slide and the next slide, you can turn off the video, see if you can answer them yourself. Once we start introducing different types of reactions, it can get a little bit confusing how to classify them. So it's really a good idea to practice. How would you classify this reaction? Well, you could immediately launch off on filling in oxidation numbers and then comparing them from side to side. So we'll do that. I mean, there's more than one way to do most everything. All right, so now you can just look at oxidation numbers and say, let's see, hydrogen is +1 on both sides. That didn't change. Chlorine is going from -1 on the reactant side to -1 on the product side, okay? And as a matter of fact, if you look at each individual element in this reaction, none of them have changed their oxidation state. So it is not a redox reaction. I'm hoping that you didn't have to go through all that and that you could see right away that it's an acid-base reaction, which are classified. Acid-base reactions are simply moving an acidic hydrogen from one substance to a different substance. And that's what this is. Here's another one. Give this one a shot. I'll walk through assigning oxidation numbers again. Here's sodium in its normal natural state, standard state, so I'll give it a 0. Oxygen -2, hydrogen +1. This hydrogen gas is in its standard state, it gets a 0. Sodium hydroxide is an ionic. So this may be a little odd here. How do we assign them for OH is OH1 -1. So that means that oxygen has -2 and hydrogen has +1, just like you like to do. All right, now let's compare oxidation numbers and see if any have changed. Sodium has gone from 0 to +1, so sodium has lost an electron. And what else has changed here? Hydrogen has gone from a +1 to a 0. Okay, so that is definitely a redox reaction, okay? We have found 2 elements that meet the prerequisite. I want to show you kind of an easy way to memorize whether or not certain types of reactions are redox or not. All right. Anytime you see a chemical reaction where you have an element in its standard state, either on the reactant or the product side, and then it changes to something else, part of a compound on the other side, that means these are redox reactions. If you keep in mind that all elements in their standard state are 0, okay, that they, by necessity, as soon as they get involved in a compound, are going to change away from 0. So this type of reaction, again, when you have an element by itself on one side or the other of an arrow, that is a redox reaction.